Here's a picture of Griffith Park Observatory looking toward downtown Los Angeles. And here's a picture from Griffith Park Observatory looking back the other direction towards the Hollywood Hills. You can actually see the Hollywood sign there in the background. Now, this is a picture of me and my dad at Griffith Park Observatory. Now, why do I want to show you a picture of my dad? Well, we'll come back to that in a moment. There is a connection here. First, let me remind you about the difference between capacitors, resistors, and inductors. So, for example, a capacitor is a device that only has a voltage across it if there's any charge stored on the plates, and that voltage would be equal to the amount of charge divided by the capacitance. A resistor is a device that doesn't store any electrical charge, but it can carry an electrical current. The greater the amount of current, then the greater the voltage across the terminals of the resistor. That voltage is equal to the resistance times the current. Well, but current is dq dt. So there are some devices that have a voltage if there's a steady amount of charge, and there's other devices, there's some devices that have a voltage if there's a steady amount of charge, and then there are other devices that have a voltage if there's a flow rate of charge. There are yet other devices, and we'll symbolize it like a diagram of a solenoid, that only have a voltage if there's a rate of change of current. In every case, there's some constant of proportionality. Here, the voltage is directly proportional to the charge, and the constant of proportionality is actually the inverse of the capacitance. The voltage depends on the rate of change of charge, and the constant of proportionality is the resistance. So there's a voltage that depends on the rate of change of current, and the constant of proportionality is called the inductance. Capacitance is measured in farads, resistance is measured in ohms, and inductance is measured in Henries. Now, what I really want to explain to you is why we throw a negative sign in this equation. So let's talk a little bit about the behavior of an inductor in an electrical circuit before we come back to this picture of my dad and I. So let's say we've got some voltage, like from a battery, and a switch that's initially open. Then there's no current flowing from point A to point B in this circuit. And so if we were to hook a voltmeter across those points, we would expect to have no voltage, and that's exactly what we get. Now let's see what happens in case 2, where we suddenly drop the switch. Then a current that starts out initially equal to 0 begins to grow, and it's going to flow in a clockwise direction. Now the current, of course, will spiral around here, come back behind this probably iron core, and then it's going to flow that way, and then back around and flow like this. But in general, it's going from point A to point B, right? Overall, the current is flowing in this way. We certainly wouldn't say that the current is flowing from point B to point A. Let's erase some of this. Okay. So is there a voltage measured from point A to point B in this circuit? If we hook up a voltmeter, will it read anything? Well, it will. The idea is if the current flows in this direction, we can use the right-hand rule. Why don't you try it? Wrap the fingers of your right hand so that they mimic the current that's flowing. I guess as an eyeball looks down on this, it would say that the current is flowing counterclockwise in that solenoid. And so magnetic field lines appear, start to point like this inside of that solenoid. Now these terms are interchangeable. We can call it an electromagnet. We can call this whole device a solenoid. Or here's a new name for it. We can call it an inductor. Well, what does Lenz's law tell us about this? Lenz's law says that the reason these magnetic when these magnetic field lines appear, that represents some flux. The magnetic field lines associated with the electromagnet, with the inductor, pass through the inductor itself. So there's a flux through the inductor, but back here, in case number 1, the flux was equal to 0. And now in case number 2, now there is some flux. Lenz's law tells us that there's always an opposition to the change in flux. Faraday's law says the change in flux can make a voltage, and that voltage would be equal to negative N times the rate of change of the flux. But it's Lenz's law that tells us the direction of the induced voltage. So we have a V, we'll put subscript B, so we've got the voltage of the battery. But then there ends up being an induced voltage because of the change in flux in the inductor. And that voltage tries to somehow compete with the current that induced that magnetic field in the first place. So as this current starts to flow, there's a opposition to that increasing current. And so a voltage shows up. Point A would be high potential, and point B would be low potential. And so you could think of the inductor itself as a potential source that's trying to make current go back the other way in a counterclockwise direction. And if the induced voltage is strong enough, then the countercurrent will cancel out the current that's flowing due to the battery to maintain the initial current at 0. As time goes by and these magnetic field lines continue to grow, then that induced voltage becomes weaker and weaker and weaker. Eventually, this counter current goes away and the clockwise current from the battery can reach its steady state value. So, what if the switch in case 3 has been closed for a long time? Then this clockwise current that made the magnetic field lines slowly start to develop bit by bit in the electromagnet, that clockwise current from the battery reaches its steady state value, and at that point there's flux, but the flux would no longer be changing. The magnetic field has reached its maximum value, so the flux has reached its maximum value. It becomes steady, and if there's no rate of change of flux, then there's no induced voltage in the opposite direction across the inductor, and the current reaches its steady maximum value. In case 3, let's suppose that that switch has been closed for a long time. Current is now flowing this way. Then really, the coils of the inductor are really just nothing more than bare wire. You might as well have a circuit with just bare wire connecting from point A to point B. And the switch is closed and current flows clockwise. Why should it matter if that bare wire is spiraled around in a coil or not? And so the voltage is 0 across the inductor in this case. And now we suddenly throw the switch back open. So these magnetic field lines that had built up and reached their max value are still here, but if you open the switch, they're going to want to suddenly disappear. But they can't disappear in an instant because of Faraday's law and Lenz's law. If these field lines were to suddenly disappear, we'd go from a case of having some non-zero flux to suddenly having 0 flux. Well, you can't make that change in flux without a voltage being induced. And so the voltage, in this case, would try to point in a direction that maintains the magnetic field or the flux that currently exists. So just before we open that switch up, current was flowing in a clockwise direction. And so the inductor is a device that says, wait a minute, I don't want there to be any change in the amount of magnetism passing through the coils. And if the reason magnetism passes through the coils in this direction was because there was a current flowing clockwise through the circuit, then the act of opening the switch is going to create a rate of change of flux that's going to induce a voltage that tries to maintain this current at a steady value. And so terminal B becomes the positive terminal. Terminal A becomes the negative terminal. And so you could imagine, what if we had a circuit that had a negative terminal here and a positive terminal here? And what way would that drive current? Yeah, it would drive current clockwise through the circuit. And so this induced voltage, in accordance with Faraday's law, makes terminal B high potential, terminal A low potential, and it maintains the current. So in this case, the source of the current is no longer the battery. The source of the current is the rate of change of flux that's taking place in the inductor. And then in case number, this was case number, 4. This is case number 5. And so if in case number 6 the switch has now been open for a long time, then now that the flux gradually made its way to 0, if it stays 0, there's no longer a rate of change of flux. There's no current flowing anymore, and there's no potential difference from points A to point B, and the voltage is 0. So when is there a voltage? Well, only in case 2 and case number 5 is there a voltage across the inductor. And I know the scribbling got a little messy at this point, but in case number 2, when the rate of change of current was positive, in other words, when it was increasing, then we found that terminal A was the positive terminal and B was the negative terminal. Now it's just the opposite here in case number 5. When we suddenly open the switch, the current decreases. So di dt would be of some negative value, and so that changed the polarity of the inductor, and A was the low potential and B is the high potential. But in all the other cases, 1, 4, 3, and 6, in all those cases, the voltage across the inductor is equal to 0. It would be just like trying to say, what's the voltage from point C to point D in this circuit? Well, if it's just bare wire between the two, there should be no potential difference at all. So why should it matter if the bare wire is in a coil? It should be that the potential from A to B is equal to 0, and indeed it is in case 6, in case 3, in case 1, and in case number 4. So why is that not the situation in cases 2 and 5? The inductor is just bare wire, so why should there be a voltage from A to B? That voltage is there as long as there's a rate of change of current. And that's the whole idea behind this equation. So there are 2 reasons why there might be no voltage. It could be because there's just no current at all flowing through the circuit, or it could be there's a current, but the current has reached a steady value. So that would be like case number 3 and case number 4. There's a clockwise current flowing through the circuit, but it's reached its maximum value and remains a steady value, and in that case, without a rate of change of current, there's no voltage at all. In case 1 and case 6, then there's also a steady amount of current that happens to be equal to 0. And so whenever current maintains a steady value, then the inductor just behaves like bare wire and there's no voltage across it. But during the moments in time when current is changing as it flows through an inductor, then the inductor actually has a voltage measured across it. So that brings us back to my dad. He looks pretty happy in this picture right here, and generally that's the case. But I can recall times in his life where he'd get a little cranky. One situation would be if the home had been empty for a long time and it was just he and my mom. But if he knew company was coming, he'd get a little bit anxious. I wouldn't say necessarily upset, but perhaps slightly agitated or slightly resistant to the idea of having a change in the way the house was going to be occupied. Just knowing that company was coming would get him on edge. And then once company was there for a while, it turned out he was the life of the party. He was the happiest person to have company there. And he got used to it, and he enjoyed everybody's company. And then the announcement was made that eventually the company had to leave, whether they were staying for a couple days or a week. Once he became aware that their vacation was coming to an end, and he realized there was going to be a change from having a lot of people in the house to none, he'd get a little bit upset about that. So it's not that he didn't like a house with no company, and it's not that he particularly always wanted company to be there. He just didn't like the change. He didn't like an increase in company, and he didn't like a decrease in company. My dad didn't like a rate of change of company. Whenever there was a rate of change of company in the house, he'd protest to some degree. In the same way, inductors put up some sort of a fight whenever there's a dt of current. It's not that an inductor doesn't like to have a current flow through it. The inductor doesn't like it when the current is increasing, and the inductor doesn't like it when the current is decreasing. Let me see if you get the idea here. Let's take case A, just a resistor connected to a battery. What would a graph of current versus time look like when we drop the switch? Well, some would say, I know how much current's going to flow. I know Ohm's law. The current is just going to be the voltage divided by the resistance, and at the moment the switch is dropped, that value just remains steady. So from time t equals 0 onward, there's just a steady amount of current flowing in a clockwise direction equal to V over R. Well, what if we replace that resistor with an inductor and take the same voltage, and here we have an inductance L. The very wire that makes up the circuit has some resistivity to it, right? So this can't, even though I haven't drawn in the symbol for a resistor in this circuit in case B, there still is some resistance to the circuit. And so the amount of current should be the voltage divided by, we'll just call this R internal. There's an overall internal resistance to all the wiring that makes up this circuit. So what does the graph of current versus time look like? Well, it turns out it's not a horizontal line. Because of the inductance, the current can't suddenly go from 0 up to some maximum value in an instant. In the same way that a car that's parked at a stoplight can't go from 0 to 60 miles per hour in an instant, it has to overcome its inertia to get up to speed. You can think of inductance as being an electrical equivalent of inertia. Current can't go from 0 to some value in an instant. Because of the inductance of the circuit, the current ultimately wants to reach its max value of V over R internal, but it can only get there gradually in time. And in fact, even in the circuit A, although we don't draw the symbol for an inductor, the fact that the wire has to make at least one loop to be a closed circuit means there's some internal inductance to the circuit. And so you really can't have a current go from 0 up to the maximum value in an instant in time. You would have to gradually get up to that value. Now, sometimes it reaches that value in such a short amount of time that we don't notice the behavior of the internal inductance, yet it's always there. Back to this circuit with the resistor, how do we determine the polarity of a resistor? If I draw a point A and a point B, how do we know which point is high potential and which is low potential? Or if I have a point A and a point B in this resistor, what's the potential? Well, it depends on which way current is flowing. If current flows to the right, then we say point A is high potential and point B is low potential. Likewise, if current flows to the left, then point B is the high potential and point A is the low potential. So how do we determine the polarity of an inductor? Well, if there's no current at all, then points A and point B are at the same electric potential and there's no potential difference. If current flows to the right, and let's say it's a steady value of current, then once again, point A and point B are at the same potential and there's no voltage. But what if current was originally flowing just a little bit to the right and is increasing, so we have some value of di dt that's positive as the current flows to the right? Then in that case, the inductor puts up a fight and tries to oppose the rate of change of current. And so it tries to drive current the opposite direction in the external part of the circuit, or in other words, the part of the circuit that's external to the inductor itself. And so that would happen if point A was high potential and point B was low potential, then it would drive a current opposite the current that's changing through the inductor. So that's exactly the case. If current flows to the right and it's increasing, then point A is high potential and point B is low potential. If current flows to the right and is decreasing, then the polarity changes across the inductor. Point B is high potential, point A is low potential. And what that would do is make the inductor act like a source of potential difference that drives current in the same direction as it was already flowing as a way to oppose the decreasing value. So there's a connection between the polarity of an inductor and Lenz's law. By the way, if current flows to the left and it's increasing, meaning di dt is positive, then can you figure out what the polarity is? Yeah, right. Point B is high potential and point A is low potential. If current flows to the left and is decreasing in value, in other words, if di dt is negative, then point B is low potential and point A is high potential. What if we have an inductor with current flowing to the left and it's constant current? Then what would you say about the potential? Right, we'd say there's no potential difference between points A and B.